Hi, this is Putipong, and I am going to present our work, RepEL, a utility-preserving privacy system for IoT-based energy meters. This work is done with Srinivasan Iyengar, Stephen Lee, David Irwin, and Prashant Shinoy. Let me begin with the motivation for this talk. Nowadays, IoT devices have become increasingly common. In smart homes, we have smart light bulbs, which can be controlled using our voice. There are smart speakers with voice assistants such as Alexa and Google Home. We have Fitbit that allows you to record your exercise, smart thermostat that can learn your temperature preferences. Although they are designed for different purposes, they all use cloud-based architecture. Most IoT devices essentially send data to the cloud to do all kinds of useful analytics and provide useful services for the user. For example, an indoor home security camera that continuously streams video to the cloud can detect people and their faces. It can send an alert if it detects any intruder when you are not at home. But you can also clearly see that this data reveal our private information. For, for example, the data that upload to the server from the camera can reveal who is at home and at what time. So to protect us from privacy leakage, there are two traditional methods. The first one is data obfuscation or data masking. The idea is to modify the original data before upload it. To give you an example, if the indoor security camera blurs the image before sending it to the cloud, it can suppress private information, such as who is in the house. But at the same time, it is also make it difficult to differentiate between the residents and intruder. The second method to prevent privacy leakage is local processing. So the idea is to not upload anything to the cloud at all and perform analytics locally. Obviously, this is safer, but it limits the ability to do some sophisticated analytics because of the lack of computational power or lack of comparative analytics across the users. So there is always a trade-off between utility and privacy. If you want one, you lost another. In this paper, we present a different approach called utility preserving privacy, which try to transform the data such that private information is suppressed and utility is still retained. So this gives us both privacy and analytics capability. In this paper, we focus on privacy in energy domain. So the main focus here is the smart meter. Let's look at the scenario. We have a house which uses electricity from the grid. The utility company somehow needs to record how much electricity each house uses so they can charge them correctly. So they install a meter at each house, and nowadays they have a sophisticated one called smart meter, which can record electricity usage data at a fine-grained granularity, like every minute or even every second. Then the smart meter will upload the electric usage data to the utility company server so they can use it for billing. The energy trace can be used for further analysis, such as energy breakdown, which can give us more detail about how we use electricity. For example, it can tell homeowners that last month they used 70% of electricity for cooking, 20% for cleaning, and 10% for others, which is useful for the homeowners. At the same time, the energy trace can be misused to find an occupancy pattern because when the homeowner is at home, they perform more activities. Then the electric usage data is going to be higher than when they are not at home, which make it possible to detect occupancy by just looking at the energy trace. And this is a privacy leakage. In fact, many sensitive information can be inferred from occupancy detection. Prior paper has shown that learning occupancy can cause a lot of privacy leakage. For example, it can tell when do you take vacation, do you eat out in the evening, were you at home during your sick leave, and many more. And these are private information that we may not want others to know. So the key question here is, how can we allow this aggregation, analytics, and at the same time, prevent occupancy attacks? So here is the outline for the rest of the talk. I already presented our motivation. Next, I'm going to introduce you to our approach, and then we will look at the experimental result and conclusion. To prevent privacy leakage from smart meter, one of the popular approaches is to use battery. The key idea is to use energy storage to transform usage seen by the smart meter. And the current state of the art is to use battery to perform data obfuscation. There are two popular techniques. The first one is called flattening. So this technique tries to maintain the load at a certain threshold by charging and discharging the battery. The way it works is, when some appliance is turned on, we supply electricity from battery instead of the grid. So the smart meter will see no change in the usage. Another technique is noise injection, which tries to add artificial power signature to the trace. Both techniques can prevent occupancy detection, but unfortunately, they make this aggregation hard or even impossible. The basic idea behind RepEL. So let me introduce you to our approach called RepEL. And the basic idea behind RepEL is to permute and randomize the order of the loads, while retain the total usage of each appliance. So RepEL use battery to suppress actual usage when it occurs, record it, and then replay it at a later time. We call this record and replay. By doing this, we retain the total usage of each appliance and at the same time permutes the time order of usage as seen by the smart meter. As a result, this can prevent time-based occupancy attack and at the same time allow us to do cloud analytics. There are 3 steps in RepEL. The first step is called record. The record module will record every foreground loads and ask battery to discharge, which will hide the loads. The next step is called schedule. The schedule module will schedule the time to replay the loads on the next time window. It can schedule based on any given target distribution. We will discuss about target distribution in detail later. The last step called replay. It will ask battery to replay the recorded loads based on the schedule and policies. Let me show you an example of how our RepEL algorithm works. Suppose that during the first time window, there are 3 foreground loads, which are microwave, washer, and television. Our record module will record them and use battery to suppress the loads. So now the smart meter will not see any original foreground loads. Next, the schedule module knows that there were 3 loads in the previous time window. So now it randomly picks 3 start times and sends the schedule to the replay module. The replay module will be the one who decides which load will replay at a given time, and then asks battery to replay that loads. As a result, smart meter will see the trace that was randomized and permute. Let's look at how our RepEL schedule the loads. We use Markov chain Monte Carlo sampling method called Metropolis Hastings algorithm, so RepEL can mimic any distribution during schedule step. For example, the left figure shows the distribution from a 1-month energy trace. This distribution allows us to observe the behavioral pattern of this house, such as washing often happens at 6 p.m. Now, if we schedule our RepEL using uniform distribution, Then the repair result will look like the figure in the middle, which uniformly scrambles the loads and also hide the behavioral pattern. Or if we use bimodal distribution, then it will look like the figure on the right, which repair most of the load during 6 to 9 a.m. and 6 to 9 p.m. This feature gives repair a freedom to schedule based on any given probability distribution. We also have vacation mode, where the homeowner is absent for a long period of time and there is nothing to record. And in this case, RepEL can replay random loads from previous week. Next is our experimental result. So we are interested to see if RepEL can prevent privacy leakage and retain utility information. So we use two metrics called privacy leakage rate and device usage change. Privacy leakage rate measures how often RepEL fails to suppress the original load. It can happen when battery is empty, so it cannot discharge to suppress the load. The ideal case is where battery can suppress all the loads or the original loads, and privacy leakage rate should be 0. The second metric is called device usage change. We want to make sure that utility is retained, so we compare the difference between the original and replay loads. For this metric, the ideal case is where there is no difference between original and replay loads, and the device usage change should be 0. In this paper, we use two datasets. The first one is data port from Pecan Street. We select 19 houses, the duration is 1 month, and the granularity is 1 minute. The second dataset is eco dataset. This dataset has ground truth occupancy data. We selected 4 houses. The duration is between 22 to 36 days, and the granularity is 1 second. In our experiment, we set time window to 1 day and used uniform distribution as the target distribution. The battery size is 13.5 kilowatt hour, which is equal to the size of 1 Tesla wall battery. The first graph on the left-hand side, x-axis shows the appliance in the house and y-axis shows privacy leak rate. On average, RepEL has less than 10% privacy leakage rate, which shows that RepEL can prevent privacy leakage. On the second graph on the right-hand side, x-axis also show the appliance in the house, and y-axis show the device usage chain. The mean across appliances for this graph is less than 3%. It shows that RepEL can retain utility. Next, we compare our RepEL with lazy stepping algorithm or LS2, which is a data obfuscation technique for smart meter. And we use non-intrusive load monitoring toolkits to disaggregate the data. This aggregation allows us to see the breakdown as shown in the graph on the left-hand side, where x-axis is the day and y-axis is the power. We can see that LS2 in the middle flatten everything and almost destroy all utility information along the way, while our RepEL on the right-hand side still can preserve the utility. We calculate mean absolute percentage error and mean square error. The results show that both errors are low for RepEL, and it is about 1 order of magnitude lower than LS2. We also compare occupancy detection accuracy on both RepEL and LS2. We use Matthew Correlation Coefficient or MCC to compare the performance, because MCC can provide a balanced measurement even when there is an imbalance in occupancy pattern. We can see that privacy varies from home to home. Both techniques have low MCC value, so both are doing well. Relatively, RepEL is slightly worse than LS2, but as we know, LS2 cannot preserve utility information. So, in conclusion, we propose a utility-preserving privacy system for smart meter called RepEL. We implemented and evaluated on 2 energy trace datasets. Our results show that RepEL can prevent time-based occupancy attack and at the same time preserve utility information in the trace. Thank you. If you have any question, please feel free to email us.